The first example is the polynomial f of g is equal to g cubed negative 1 is equal to g negative 1 times g squared plus g plus 1 has a 0 over order m, which is equal to 1 at g naught is equal to 1. Since f of g can be expressed by this two parts, g negative 1 times g of g, where g of g is equal to g squared plus g plus 1. Because f and g are entire, and g1 is, because we just insert here 1, then 1 plus 1 plus 1 is equal to 3. So g of 1 is equal to 3, which is not equal to 0, non-zero. So by the theorem, f of g has a 0 of order 1 at g naught is equal to 1. However, we can determine the order of the 0 for the given function g naught is equal to 1. It's the 0 of order m is it is a 0 of order m is equal to 1 of function f, by using the theorem. Just the observations here. F is entire, so f1 is 0, but f'1 is not 0, which is the 3. We can easily evaluate this f prime g here. 3 times g cubed g squared. Then we just input 1 here, then we get 3. So f1 is equal to 0, but f'1 is not equal to 0. So the g naught is equal to 1 is a 0 of order m. We can see that. The second example is that entire function f of g is g times e to the g negative 1 has a 0 of order m, which is equal to 2 at the point g naught is equal to 0. Since f of g and f prime of g is equal to 0, but f double prime of g, f double prime of 0 is equal to 2, which is non-zero. In this case, we have f of g can be expressed like this: g negative 0 to the squared times g of g, where g is entire function here. Here. Here make a modification. With this given function f, g squared times actually some function g of g here defined by this. When g is not equal to 0, g of g is defined by this: e to the g negative 1 divided by g. When g is equal to 0, the value of function of f of g of g is equal to 0, equal to 1. We just checked it in example 1 in section 71. Okay, next theorem states that the fact that precisely analytic function f of g has only isolated zeros when it is not identically equal to 0. This means that if g0 is a zero of such a function f of g, there is a deleted neighborhood. The absolute value of g negative g0 is greater than 0 and less than epsilon of g0, in which f of g is non-zero. Okay, theorem 2 says that given a function f and a point g0, suppose that A, f is analytic at g0, B, f of g0 is equal to 0, but f of g is not identically equal to 0 in any neighborhood of g0. Then f of g is not equal to 0 throughout some deleted neighborhood given by this. Absolute value of g negative g0 is greater than 0 and less than epsilon of the point g0. Okay, let's prove it. To prove this theorem, let's first assume let f be as stated and observe that not all of the derivatives of f at g0 are 0. If they were, all of the coefficients in the Taylor series for f about g0 would be 0. And that would mean that f of g is identically equal to 0 in some neighborhood of g0. So it is clear from the definition of zeros of order m at the beginning of this section that f must have a zero of some finite order m at g0 according to theorem 1. Just we check it. Then we have this f of g is equal to g negative g0 to the power of m times g of g. Here g of g is analytic and non-zero at g0. Now g is continuous in addition to being non-zero at g0 because it is analytic there. Hence, there is some neighborhood. The absolute value of g negative g0 is less than epsilon, in which equation 4 holds, and in which g of g is not equal to 0. Consequently, f of g is not 0 in the deleted neighborhood given by this. So the proof is complete. Next is the theorem 3. Given a function f and a point g0, suppose that a and b, f is analytic throughout a neighborhood n0 of g0. Here, look at figures. Here, n0 means this area. Circles interior to the circle, centered at g0 here. B f of g is equal to 0 at each point g of a domain D, while line segment R containing g0. Then we have that result, this result, f of g is equal to 0 in the neighborhood n 0, that is f of g is identically equal to 0 throughout the neighborhood n 0. Okay, let's prove this theorem. We first observe that under the condition, this condition, f of g is equal to 0 in some neighborhood n of g naught. For otherwise, there would be a deleted neighborhood of f g naught throughout which f of g is not equal to 0. According to theorem 2, because we just, here we get the result from theorem 2. And that would be inconsistent with the condition that f of g is equal to 0 everywhere in a domain D or on a line segment R containing g naught. Since f of g is equal to 0 in the neighborhood n, then it follows that all of the coefficients an, which is equal to nth derivative of f at g naught divided by n factorial, where n from 0 to 0, 1, 2, keep going, which is a natural number, non-negative numbers, non-negative integers, in the Taylor series for f of g about g naught must be 0. Thus, f of g is equal to 0 in the neighborhood and 0, since the Taylor series also represents f of g in the neighborhood and 0. So this completes the proof.